And we are going to be talking about light and how scientists use light to make measurements. And as we talk about that, we're going to be discussing what's called the electromagnetic spectrum. Has anyone heard of that before? If so, raise your hand. Okay, electromagnetic spectrum is the way that we describe radiation that moves through the Earth's atmosphere. And we think of these as energy waves. And the name electromagnetic reflects that we have both electric and magnetic fields associated with these waves. Now, over on the left-hand side of this slide, we have the really short, high frequency, high energy region of our electromagnetic spectrum. Gamma rays and X-rays are really, really high energy, and they can actually cause atoms to ionize. And that ionization can cause harm to our bodies. As we start to move from left to right, we then go to the ultraviolet region of this spectrum. So that's pretty high energy radiation that we get from the sun. And this kind of radiation can cause sunburns and in more extreme cases, even skin cancer. So we wear sunscreen and sunglasses and hats, and we protect ourselves from that ultraviolet radiation from the sun. Next, we have the visible region of the electromagnetic spectrum, and this is a really narrow band of wavelengths from 400 to 700 nanometers long. And this is the small region of light that we can actually see with our eyes. So there's lots of light and lots of energy around us that we can't see, and it's this little piece that we can see. And within this, I want to point out that it's the blue and the purple wavelengths that are higher energy and the red that's lower energy. And then we have longer and longer wavelengths, infrared, microwaves, and so on. So what creates light? I'm going to ask Delaney, a graduate student in my research group, to share with us a little bit more about what causes light and different colors of light.
Yeah, thank you. So now I'm going to talk about flame test. Flame test is a test we used in chemistry to identify the presence of some metal ions. So as you can see in this picture, different elements give different colors because of their unique emission spectrum. So then we'll talk about a little bit real life application of this science. Have you ever wondered how fireworks produce beautiful colors? Simply, that is because of emission of light from metals due to high temperature in the fireworks. So these fireworks contain either one metal or combination of different metals. Because of that, they give wonderful colors. So then let's see how this happens in an atomic level. So in the next slide, here you can see the emission spectrum of hydrogen at the top, and at the bottom you can see the nucleus of hydrogen atom and its energy levels. So electrons in this atom can absorb energy, energy from external sources like heat, and they are promoted to higher energy level. So in higher energy levels, these electrons are unstable. So they come back to their lower energy levels and release their energy. So elements actually releases this energy in the form of electromagnetic energy with a particular wavelength. So we can see their unique colors. So each element's emission spectrum is unique. So in the next slide, we have shown you different emission spectrums of different elements like helium, mercury, and uranium. So with this basic knowledge, now we are going to move into our light bulb activity.
All right, well, I hope what you can see behind me is a table with a couple of different light bulbs on it. So what I'm going to do is I'm going to turn off my overhead light so we can look a little bit more closely at all of these light bulbs. So we're going to look at a couple different kinds of light bulbs. We have an incandescent, a compact mercury fluorescent, a light emitting diode or an LED, a bug lamp, and a black light. Now, I hope you have a worksheet that came along with your activities for today that has this picture on the front. It also has an electromagnetic spectrum. What I'd like for you to do is pull out that worksheet, and we're going to take some notes and make some observations as we go along. So the first kind of light we're going to look at is an incandescent light bulb. And what I'm going to do is share my screen now. And we're going to take a look at this light bulb through a device called a diffraction grating. And a diffraction grating can take the light from one bulb and separate it out into the different wavelengths. So this first light bulb is turned on, and we can see the white light right here in the middle. And then off to the side, we see a really bright patch of light that looks a little bit like a rainbow. Now, if I turn this a little farther, we can see the second diffraction, and that one is right here. And this, the second one, let's see, right in front of my hand, is actually a little bit more spread out, and you can see the colors defined a little bit more. Now, an incandescent light bulb is one that it heats up. There's a tungsten filament inside, and as it gets really hot, it emits all of the colors in the rainbow. And that's similar to our sun that gives us the full spectrum of visible light. Now, what I'm going to do next is ask that you guys note on your worksheets that we get to see all of the colors of the rainbow from this incandescent light. Another thing I want to mention is this light bulb is a light bulb that gets very hot very quickly. We're actually going to measure the temperature of it a little bit later, but it gets really warm. Now let's go on to our next light bulb. This is a mercury fluorescent light. Now I'd like for you all to unmute yourselves and let me know, what do you see when you look at the light that's emitted from this particular bulb? You can make observations about shape, about intensity, how bright it is, what colors do you see? I'd love to hear from you. Go ahead and unmute and tell me what you see here.
I see some reflections of the light.
Yeah, you see some reflected light. What else do people see?
Are you talking to me?
Anyone else? Or yeah, anyone. Go ahead and share your observations.
Okay. So yeah. So what observation people see?
So what colors do you see in
Red,
this light bulb?
green, and blue.
Red, green, and blue. Does anyone else see other colors?
I see a little bit of orange in between the red and green.
Yeah, a little bit of separation. And how about the shape? What shape of light do you see?
It has the same shape as the light it's reflecting.
Yeah, it does have the same shape as the light bulb. And that's great. So we've noticed now we have a different kind of light bulb. This light bulb is full of mercury gas. And as that gas gets excited, it emits very specific wavelengths of light. Now the light bulb is coated in a material called a phosphor, and that then turns that ultraviolet light, which is too high energy for us to see, and it turns it into different colors of light. So from this bulb, you actually get red and yellow and blue, and they combine back together to turn into white light. Now this is an example of a line emission spectrum where we get discrete colors, but not a continuous. All right, so next we have an LED, and I want you to look at this second diffraction right here. And what do you see in this case? What do you observe? What colors do you see?
It's the full rainbow again.
All right, so you see all these colors that are emitted by this bulb, and the bulb appears white, and when those combine, it gives us the white light. Now, an LED is made of materials that emit kind of broad bands of light, and those combine together to make white light. Now, the last one I want to show you is a compact fluorescent lamp that has a filter on it. And so this is called a bug lamp. And this one has a yellow coating. And what do you notice about the light coming from this bulb when you look at the individual colors? Are there any colors that are missing from the rainbow?
It's missing blue.
It is missing blue. And that's kind of an interesting thing. It turns out that the bugs can actually see blue and purple light, but they can't see these longer, lower energy wavelengths. And so we might put this kind of lamp on our porch where we want to have light for us to see, but something that won't attract bugs. So this could be a good option if you want to have light but keep the bugs away. Okay, so hopefully in all of your packets of materials that you got for today, you got a little device called a diffraction grating, which is, it looks a little bit like this. Okay, I'd like for you to pull those out, and we're going to go into 3 breakout rooms, and you're going to work with a graduate student to get your diffraction gratings working so that you can see light coming out of different bulbs in the room that you're in, and examining a light bulb in your environment. So we're going to go into some breakout rooms, and let's see. You should be getting a note to go ahead to those breakout rooms, and then we'll start our next part of our activity. Welcome back. Was everyone able to get their diffraction gratings to work? Awesome. All right, welcome back, everybody. So we're going to go on to the next part of our activity, and I want you to flip to the back side of your worksheet now. I had mentioned earlier that, well, I got a question of what are we supposed to write on the paper? You can write along any observations or notes as we go along. What we're going to do next is actually add a little bit of data into the table on the second side of the worksheet. So flip to the back if you haven't yet. And I mentioned earlier that one of our light bulbs gets really, really warm. So we want to look a little bit closer at that particular observation. So what I've done here is I've set up my light bulbs with a thermocouple, which is a fancy way of saying a thermometer. And we're going to go ahead and measure the temperature of these light bulbs. And we're going to use the units of Fahrenheit today because that's the temperature that we oftentimes think about when we turn on our ovens or check our own temperatures. And we're going to compare the temperatures of an incandescent light bulb and a LED. So for the incandescent light bulb, the temperature that I see is 314.2 degrees. And it's fluctuating just a little bit, but that's a pretty hot light bulb after just a couple of minutes of being on. So why don't you go ahead and record 314.0 or 314.2 for that temperature. Now I'm going to switch and look to my next light bulb. This is the LED. It's 101 degrees, 101.8, much, much cooler. Well, I want to point out that our incandescent bulb requires 60 watts of energy. So that's quite a bit of energy in order for it to turn on. Our LED, on the other hand, is even brighter. It gives us more light, but it only requires 9 watts of power to turn on. So we have a light bulb in the case of the LED that creates a lot of light for less energy, and that makes it more efficient. So one of the questions I want you to think about is, well, this incandescent bulb uses a lot more energy, and it doesn't give us that much more light. Where is all that energy going? Well, from these measurements, we might think that some of that energy is being turned into heat and would cause our light bulbs to get warm. Okay, so I'm going to stop sharing and I'm going to turn it over to Ethan, who's going to give us a little bit more information. And to our other presenters, I think we'll just wrap up after Chamari and I'll make a few closing remarks, okay? So Ethan, we'd love to hear from you next.
So we went through and talked about all the different kinds of light sources. From the people in my breakout room, it sounded like we had a lot of light emitting diode bulbs, which is great because they're a lot more energy efficient. But what I want to talk about next is why you should never look at the sun. And the sun emits all sorts of radiation in the electromagnetic spectrum. So ranging all the way from the highest energy radiation all the way to the lowest energy radiation. We call this a black body radiator. And part of the emission spectrum from the sun includes UV rays, which come to Earth. And those UV cause sunburns if you're not wearing sunscreen on a summer day. And if you take a look at the sun without any necessary protection, that can cause the same sort of damage to your eyes as it would to your skin. So you can essentially get a sunburn inside your eyes. So that's why you should never look at the sun.
Yeah, so I am going to talk a little bit about how I use the electromagnetic spectrum in my research. So have any one of you heard about pollen allergies? So this pollen allergies happens when the pollen grains that are present in the air goes into our respiratory system. So we can see these pollen grains under the light microscope, which uses the visible light. But in the presence of water, like when it rains, these pollen grains can rupture or burst open to release small pollen fragments. These pollen fragments are so small, so they can reach into the deeper levels of our lungs to cause severe asthma symptoms. So it is important to understand how these pollen fragments looks like, but we can't do it with the limitations of the light microscope. So in order to do that, we use another microscope known as the scanning electron microscope. So it uses a beam of electrons. This microscope helps us to look at the pollen fragments, measure their sizes, look at their shapes, and understand how these pollen fragments looks like. So that is how I use the electromagnetic spectrum in my research.
All right, well, thank you, Chamari, and thank you everyone for joining us this morning to learn more about light and how we can use light to make measurements of our atmosphere and even outer space. So hopefully you received one of these workbooks or a magazine in your materials for today. There's lots more activities that you can try at home. And you also received some beads that are sensitive to ultraviolet radiation. So these will turn color when you expose them to that high energy UV light. And we've encouraged you to think about what kinds of experiments you might do with these at home. We didn't get time to talk about that today because we're running out of time, but I really want you to play around with these. They are a lot of fun. So thank you very much for joining us. I know you've got lots of other fun things to do this morning. So if you're just finishing up this session, you can go ahead and exit and join your next one. And if you're just joining us for the atmospheric chemistry session, please stick around. We'll get started in a couple minutes. So thanks everybody. Have a good morning.